In this module, we will look at a family of distributions called the generalized linear model. We will look at the components which make up this model. The first will be the exponential family of distributions. Now recall, when we looked at linear regression, we always assumed normality, and now we want to generalize the concept of regression beyond the case where the outcome is normally distributed. We shall generalize to the concept of the exponential family. We shall introduce this family, look at the structure of the density or mass function, and see that it has some common properties. We shall look at some popular examples which will include the Poisson, the binomial, and also the normal as a special case. Finally, we will look at the structure of the likelihood and the score equations and the information matrix. Learning objectives for this module. We shall first introduce the exponential family. Next, we shall look at its properties. To relate to the concept of regression, we will introduce the concept of link functions, and finally, we shall look at the details of maximum likelihood estimation for the one parameter exponential family. The exponential family is specified by the probability mass function or the probability density function of the form given on this slide. Given a parameter theta and an optional parameter phi, f of y theta phi is equal to exponential y theta minus b theta by a phi plus c of y phi. Theta here is the parameter indexing the family and is called the canonical parameter. We shall see, using some examples in a subsequent slide, that the canonical parameter can be slightly different from the natural parameters we use to index some commonly known families such as the Poisson and the binomial, which are all special cases of the exponential family. Phi is a scale parameter, and note that it is optional in the sense that it may or may not be present. In fact, for very two common examples such as the Poisson and the binomial, there is no additional scale parameter. The normal distribution is an example of an exponential family which includes a scale parameter. In this definition, the functions b, a, and c are all assumed to be known. The one parameter exponential family has some key properties. First, it is possible to show quite easily that for this family, the expectation of y exists and is given by b dash theta. The variance is given by b double dash theta into the function a of phi. Note that the likelihood of theta and phi is given by log likelihood equal to log of f y theta phi, which is equal to y theta minus b theta by a phi plus c of y phi. This means that the score equations are given by del L del theta equal to y minus b dash theta by a phi, and the second derivative is given by del square L del theta square equal to b double dash theta by a phi. Now, using the properties expectation of del L del theta equal to 0 and expectation of del square L del theta square equal to minus of expectation del L del theta whole square, which we know hold under some very general regularity conditions, we get that expectation of y minus b dash theta by a phi equal to 0, implying that expectation of y is equal to b dash theta. Also, that expectation of del L del theta whole square, which is equal to expectation of y minus b dash theta squared by a square phi, is equal to variance of y by a square phi. Using these two, we are able to derive the expressions for the mean and the variance given on the earlier slide. The binomial family is a very common example of a one-parameter exponential family. Now, suppose that y is the corresponding proportion, then the density is given by f of y theta phi equal to m choose my pi to the power my into 1 minus pi to the power m minus my. Now, it is quite natural to index the binomial family in terms of the proportion pi. However, note that to get it into the one-parameter exponential form, we write it as exponential y log of pi over 1 minus pi plus log of 1 minus pi divided by 1 over m plus log of m choose my. Equating this to the one-parameter exponential mass function, we see that the coefficient of y is given by log of pi over 1 minus pi. This means that the canonical parameter for this family is not pi, but is given by theta equal to log of pi over 1 minus pi. Log of pi over 1 minus pi is termed as logit of pi. The function b theta, which is equal to minus log 1 minus pi, or in terms of theta, is log of 1 plus e to the power theta. The function c of y phi is log of m choose my. Note that the parameter is indexed by a single parameter only, which means that there is no additional scale parameter, and a phi is a constant 1 over m. This means that for the binomial family, the scale parameter phi can be taken as identically equal to 1. The Poisson family is another common example of the one-parameter exponential family. For this family, the mass function is given by f of y theta phi equal to e to the power minus lambda, lambda to the power y by y factorial, which is equal to exponential y log lambda minus log of y factorial. As before, the canonical parameter for this family turns out to be theta equal to log lambda. The function b theta is given by b theta equal to e to the power theta. C of y phi is equal to minus log y factorial, and as before, there is no additional scale parameter, and a phi is equal to 1. The Gaussian family is also a special case of the one-parameter exponential family. Here, as you know, f of y theta phi is equal to 1 over root 2 pi sigma square exponential minus 1 over 2 sigma square y minus mu whole square. Expanding this, we can write it as exponential y mu minus mu square by 2 by sigma square minus half into y square by sigma square plus log of 2 pi sigma square. Here, the canonical parameter is equal to mu, so we have a situation where the canonical parameter is equal to the natural parameter. B theta is given by theta square by 2. C of y phi is equal to minus half y square by sigma square plus log of 2 pi sigma square. However, note that we do have an additional scale parameter sigma square, and a phi is equal to sigma square. However, our objective is not to look at the outcomes only, but to relate them to a p vector of covariates. To this extent, we define the linear predictor eta equal to x prime beta, where x denotes a p vector of covariates and beta an unknown vector of regression coefficients. The link function then relates the covariates to the outcome through eta is equal to g of mu. The variance function is something unique for the one parameter exponential family. You will note that both for the binomial and the Poisson, the moment the mean is known, we are able to specify the variance. The variance function thus is a function v of mu such that variance of y is equal to v of mu times some indicator a phi. Canonical links. Canonical links arise when theta is equal to eta. For the Gaussian family, this leads to the identity link g of mu equal to mu. For the binomial family, this leads to the logit link g of mu is equal to logit of mu, where mu is the binomial proportion. For the Poisson family, it leads to the log link g of mu is equal to log of mu, where mu is the Poisson rate parameter lambda. The variance functions are specified by, for the Gaussian family, v of mu is equal to 1. For the binomial family, v of mu is equal to mu into 1 minus mu. And for the Poisson family, v of mu is equal to mu. In a future module, we shall look at situations where the empirical variance turns out to exceed the variances specified by these formula. In such cases, we have a situation of over-dispersion or under-dispersion, and we need special techniques for this case. These will be discussed in a future module on quasi-likelihood estimation. It is possible to think of alternative link functions. The canonical link is often used as a default choice in the software. One reason for this is that it leads to relatively simple likelihood equations. Another reason is that the sufficient statistics in this case turn out to be linear functions of the y's, and convergence properties are better. However, as you have noted from the module on binary choice, in many situations mathematical formulation alone will not be satisfactory for choosing the link. In such cases, we can think of alternative links. So, for example, if we have a binomial family, we know that the canonical link is the logit given by g mu equal to log of mu over 1 minus mu. However, it is also possible to think of alternative choices such as the probit link, where g of mu is equal to capital phi inverse of mu. Another reason for preferring the logit to the probit is that the regression parameters for the logit are readily interpretable as log odds ratios, while for the probit, although we can look at the predicted values of mu, the coefficients beta have no ready interpretation. A third alternative possibility is the complementary log-log link specified by g of mu equal to log of minus log 1 minus mu, and in this case too, the estimated regression parameters have an attractive interpretation as log hazard ratios. The score function for the generalized linear model can be written for the jth component of beta as Sj beta summation 1 to n, assuming that there are m individuals, xij by g dashed mu I, a phi v mu I whole inverse into yi minus mu I. In vector matrix form, this can be rewritten as summation I 1 to m del mu del beta prime a phi v mu I whole inverse into yi minus mu I. The information matrix has the following expression. Fisher's information, which is minus expectation del s beta del beta, is equal to summation over I del mu I del beta prime a phi v of mu I whole inverse del mu I del beta. Of course, for purpose of inference, we would replace beta by the estimated beta hat. The observed information is given by minus del s beta del beta, and this can be shown to be I beta minus summation I 1 to m del ai del beta into yi minus mu I of beta. You can note that in the situation where we have used a canonical link, the second term will disappear, so that for canonical links, the Fisher's information and the observed information can be shown to be equal. The asymptotic distribution of beta and phi can be calculated by observing that the information matrix for beta and phi is a block diagonal matrix of the form I beta 0 0 I phi, where I beta is equal to minus expectation del s beta del beta, which as before is equal to summation over I del mu I del beta prime a phi v mu I inverse del mu I del beta. Asymptotically, the ML estimators will be distributed as p-dimensional multivariate normal with true mean beta, where beta is the true parameter, and covariance matrix I inverse beta. In a subsequent module, we should look more closely at the details of solution of these score equations. In this module, we have introduced the components of the generalized linear model. This involves generalizing the concept of regression to the one-parameter exponential family, which may or may not include an optional scale parameter. We have introduced this family and looked at the structure of its mass function or density function. We have seen that the components of this function have some special relationships to the mean and the variance. We have also introduced the concept of a canonical parameter and thereby the concept of a canonical link. We have introduced the variance function, and in a subsequent module, we shall see that this variance function is not obeyed empirically by all data sets. In this case, we will look for remedies, and these are summarized in the module entitled Quasi-Likelihood. Finally, we have looked at some common families such as the binomial, the Poisson, and the normal, and seen that they are all special cases of the one-parameter exponential family.